So today we're going to talk about section 1.4, which is on a differentiation rule that pertains to composition of functions. It's called the chain rule. So the statement of the chain rule is as follows. So we're going to let m of x be e of I of x. So you'll notice that this is one function, namely I of x, plugged into a second function, which is e of x. So this is the notation that your author uses here. I stands for the interior function and E stands for the exterior function. Very frequently you'll hear these called the inside and outside functions respectively. So we have to assume here that both the inside and outside functions are differentiable. And if that's the case, then this composition of functions is also differentiable, and moreover the derivative of m in this case, m prime, is the derivative of the outside with the inside plugged in, all multiplied by the derivative of the inside function. So you'll notice here that the inside function, when it's plugged into the derivative of the outside function, doesn't get touched. In particular, this is not the derivative of the outside times the derivative of the inside, or anything like that. The chain rule can be a little bit confusing when it's written in this form. It'll be a little bit more clear once we go over the first example. If we're going to use Leibniz notation, we can let y be the exterior function, but this time we're going to change the independent variable to a u. And then in turn, u is itself a function of x, so u equals I of x. Then the chain rule in Leibniz notation is dy by dx equals dy by du times du by dx. You'll notice on the left-hand side here that if you treat these derivatives as if they were quotients, then you could just cancel out the du's and you'll be left with dy over dx. That's the power of Leibniz notation. It tells you what the chain rule is if you just think of derivatives in terms of quotients. So let's hit the first example here. In this example, we want to differentiate the following composite functions. In part 1, m of x equals the quantity 2x cubed plus 4 all raised to the minus fifth power. In part 2, m of x is e to the power 3x to the fourth plus 6. And in part 3, m of x is ln of x squared plus 9x plus 4. So from here I'm going to change to a whiteboard application on my iPad and we'll go through this by hand. So first we're going to work our way through the first part of the first example. And in this example, our function that we're trying to differentiate is m of x, which is the quantity 2x cubed plus 4, all raised to the minus fifth power. So you'll notice here that 2x cubed plus 4 is the inside function, that is I of x. And that raising to the minus fifth power is the outside function, the exterior function as your book would call it. So here I of x is 2x cubed plus 4, and e of x, the exterior or outside function, is x to the minus fifth power. So in order to find the derivative of m here, we first need to find the derivative of the exterior or outside function, which in this case is a simple application of the power rule. We slide the minus 5 down in front, subtract 1 from the exponent that used to be there, and we get e prime of x is minus 5 times the quantity x to the minus sixth power. In a similar way, now what we're going to do is take that interior function, I of x, and plug it into e prime. In other words, everywhere we see an x in e, we're going to replace it with I of x. So what we get in that case is minus 5 times the quantity 2x cubed plus 4 all raised to the minus sixth power. You'll notice that there used to be an x in e prime of x. Now we've plugged I of x into x in e prime to get minus 5 times the quantity 2x cubed plus 4 all raised to the minus sixth power. Next up, we need to differentiate the inside function, I prime, which is 6x squared. The chain rule says that the derivative of m is the derivative of the exterior function, or the outside function, with the inside function plugged in, all multiplied by the derivative of the inside function. Now, we put all of these pieces together, and what we get is m prime is negative 5 times the quantity 2x cubed plus 4, all raised to the minus sixth power, multiplied by the derivative of the inside, which in this case is 6x squared, which we found out above. We can simplify things just a little bit, make it a little bit prettier to get minus 30x x squared times the quantity 2x cubed plus 4 quantity raised to the minus 6th power. That's about as simple as it's going to get, and that's our final answer. Now, that being said, nobody actually applies the chain rule like this. There's a much faster way of doing this problem. So what I'm going to show you now is an alternate solution, and this is the way that you want to think about the chain rule. So we're going to start back at the beginning with our original function m of x, which is 2x cubed plus 4 all raised to the minus 5th power. Now the very last operation that occurs here is raising to the minus 5th power. That's the first operation that we're going to differentiate. So we're going to treat this as exactly as if it were just a power function. We're going to take that minus 5 and we're going to slide it down in front, and we're going to subtract 1 from the exponent that used to be there. And what we end up with when we do that is minus 5 times the quantity 2x cubed plus 4 all raised to the minus 6th power. Now you'll notice there that I did not touch the interior function. It remains 2x cubed plus 4 all raised to the minus 6th power. And then at the very end, we multiply by 6x squared. That is the derivative of the inside function. Once again, we can simplify a little bit, and we get minus 30x squared times the quantity 2x cubed plus 4, all raised to the minus 6th power. Now, at this point, your head is probably spinning a little bit. So we're going to go through the next part of this example and follow along with me once again. Once we get done with that, you're going to give the third part of this example a shot all on your own. So in the second part of this example, we start with the original function m of x, which is e to the quantity power 3x to the 4th plus 6. So we're going to differentiate this guy using the chain rule. We're going to take the derivative of the outside function. And remember, the derivative of e to the x is just itself. So you'll notice here that I do not touch the inside function. In particular, I don't take its derivative yet. So the derivative of the outside function, e to the whatever, is just itself, e to the whatever. And I don't touch that inside function. And then at the very end, I multiply by the derivative of the inside function, which in this case is 12 times x cubed. Now we can rearrange things just a little bit here by commutativity of multiplication to get 12x cubed times e to the 3x to the 4th plus 6th power. That's about as simple as things get in this case, and that's going to be our final answer. Now, what you should do at this point is take a look at the third part of this example. In this case, the function is m of x is ln of x squared plus 9x plus 4. Try to differentiate it yourself. Pause the video at this point and give it a shot. Once you're through the problem, unpause the video and watch the solution that I give for this problem. So now that you've gone and tried to find the derivative all on your own, let's go and find the derivative together. So in this case, we're looking for the derivative of m. Now notice that the outermost function here is a natural log function. The derivative of natural log of whatever's on the inside is 1 over whatever's on the inside here. You'll notice that once again, I do not touch the inside function yet. The derivative of ln of x is 1 over x. In this case, it's ln of something more complicated, in particular x squared plus 9x plus 4. The derivative of that is 1 over the inside, which in this case is x squared plus 9x plus 4, but I do not touch the inside function. And then finally, by the chain rule, I multiply that by the derivative of the inside. The derivative of x squared plus 9x plus 4, in this case, is 2x plus 9. Now once again, we can make things a little bit prettier by combining these fractions together to get the quantity 2x plus 9 all divided by x squared plus 9x plus 4. That's about as simple as it's going to get in this case, and that's our final answer. Next up, what we're going to start to do is to combine all these different differentiation rules that we have together. So we're going to be applying the product rule and the quotient rule and the chain rule all at once. This is where things really start to get nasty and where we require really a lot of just drilling where it comes to derivatives. So when you're combining different differentiation rules, The rule that you apply first corresponds to the last operation that would take place in this particular function. So last operation by order of operations, that is by PEMDAS. So let's say, for instance, that multiplication is the last thing that would have happened in PEMDAS. That's the first thing that you would differentiate. So if it's multiplication last, you apply the product rule first. If it's division last, you apply the quotient rule first, and so on down the line. So when you have multiple nested functions, one function inside another function, inside another function, and so on, what you're going to do is apply the chain rule over and over again, and you're going to go from the outermost function towards the innermost function. In fact, this is where the chain rule gets its name. You're going to chain the differentiation together over and over again. Really, it doesn't take more than one step, but it can be a little confusing the first time you see it. The most important thing that you can do when it comes to these derivatives is practice. So I'm going to post a drill on eCampus. It'll be a PDF file, and basically you're just going to go over differentiating a whole bunch of different functions. Make sure that you're concentrating very hard on the homework. Make sure that you do this drill. Taking a derivative quickly and easily is a fundamental skill that you need to have when you walk out of calculus. And it's a skill that we're going to build on for the rest of the semester, really. So make sure you have this down, otherwise later on you're going to be worried about taking a derivative when you should be worried about optimization or something like that. So what we're going to do next is another example. And in this example, we want to differentiate the following functions. In the first part, we want to differentiate e to the quantity quantity 1 plus ln of x, and that entire quantity squared. So notice there's a series of nested exponents here. E to the, and then that bracketed term squared. In part 2, y equals the quantity ln of 1 plus e to the x, quantity to the third power. In part 3, in the numerator, so we have a rational expression here. In the numerator, we get 5x minus 4 quantity to the 7th power, all divided by x plus 6. And finally, in the fourth part, the square root of x times ln of the square root of x. So in this first example, part A, the function that we're looking to differentiate is e to the quantity 1 plus ln of x quantity squared. So there's this sort of leaning tower of exponents here. So we're going to pull this thing apart one step at a time, which is how you want to handle this the first couple times that you practice on the chain rule. What we're looking for is the very last operation that would take place by order of operations if we were to plug in an x value. So imagine I handed you x equals 3. The first thing that you would do in this function is take that 3 and you would plug it into ln. ln of 3, whatever that number happens to be. You would take that, you would add it to 1. You would take that quantity and square it, and then finally you would take that quantity that you just got from squaring, and you would raise e to that power. Done. So the last operation that takes place here is e to the blank. As a result, that's the first operation that we differentiate. In particular, the rule that we're applying here is the rule for differentiating an exponential function, e to the whatever. So what I'm going to do is peel this apart one piece at a time, going through the chain rule one step at a time. Think of it a bit like an onion. You peel off the last layer and then you have an onion, and then you peel off the next layer and you still have an onion, and then you peel off the next layer and on and on and on until you have no more onion. So we're going to differentiate this last operation first. So the first thing that we differentiate here is e to the whatever. And what that looks like is the following. Remember, e to the whatever is its own derivative. So in this case, y prime is just e to the whatever. But what the chain rule says is then we have to take the inside function, which in this case is that bracketed term squared, and we have to multiply by its derivative. So the way that I've written this here is I've just written that inside function prime. That's peeling off that first layer of the onion and you still have an onion underneath. In other words, we still have a derivative to take. So the next step, we're going to take the derivative of what's inside those parentheses with the prime on it. The last operation that occurs inside those parentheses is the squaring operation. So that's what we're going to differentiate in this next step of peeling back this next layer. So anytime you differentiate something squared, that 2 slides down in front, don't touch the inside, and then you subtract 1 from the exponent that used to be there. So what we're left with is that same exponential quantity to start with, but then multiplied by 2 times that bracketed term, which is 1 plus ln of x, all raised to the first power here. Now, we're still not done because the chain rule then says we have to multiply by the derivative of the inside of that bracketed term. So we have to multiply by bracket 1 plus ln x prime. Now you'll notice here that I say don't touch the inside because you do not want to differentiate the inside here. What you want to do is multiply by the derivative of the inside at the very end, which is what we've done here. Next step, we need to differentiate that term in brackets. And this is a sum rule. The last operation that would take place here is that addition. So we differentiate the 1, we differentiate the ln of x, and then we add those two derivatives together. Now we're going to start back up on the next line here. And what that's going to look like is everything that didn't have a prime on it looks exactly the same. The only thing that changes is this very last term here. And what that is the derivative of 1 plus ln of x. We can rearrange things a little bit to make it a little bit prettier here to get 2 over x times bracket 1 plus ln x times that exponential quantity that we originally started with. That is our final answer, and that's the derivative of the original function. So what you want to do next is take a shot at part B of this example. See if you can differentiate this one small step at a time. Go ahead and pause the video and come back when you've given it a shot. So now that you've attempted to do this derivative yourself, let's go ahead and go through it together. So you'll notice here that that cubing, that third power, is the very last operation that would take place by PEMDAS. As a result, it's the first thing that we differentiate. So we slide that 3 down in front. We multiply it by the inside. You'll notice here that we did not touch the inside function. You never want to differentiate that inside function. Eventually you're going to multiply by its derivative at the very end. So we didn't touch the inside. We subtracted 1 from the exponent that used to be there, leaving a 2. So 3 minus 1 is 2. And then at the very end here, you'll notice we multiply by the derivative of the inside. That is, we multiply by the inside prime. Now, the inside is ln of 1 plus e to the x, whose derivative is 1 over 1 plus e to the x. But we again have to apply the chain rule at the end here, and we have to multiply by the derivative of 1 plus e to the x, which is itself e to the x. So what we end up with, when we put all this together, is 3 times that bracketed quantity squared times 1 over 1 plus e to the x times e to the x itself. This is why we call this rule the chain rule, because it just chains. You take the derivative of the inside, but to do that you got to take the derivative of the inside, but to do that you got to take the derivative of the inside, and so on down the line. So there's a lot of chained derivatives there. So next up we're going to take a look at part 3 of this example, and in this case we have a quotient. Quantity 5x minus 4 all raised to the 7th power divided by x plus 6. Division here is the last operation that would occur, so it's the first differentiation rule that we have to apply. Namely, here we have to apply the quotient rule. So go ahead and pause the video at this point. Take the derivative of this function, or at least give it a shot. When you've given it a shot, come back and we'll go through the solution together. So now that you've given the derivative of this one a shot, let's go ahead and take the derivative. So you'll notice here that the last operation that takes place is the derivative, and as a result, what we have to differentiate first is that, division. So we're going to apply the quotient rule first here. So this is low d high minus high d low, all divided by low squared. So you'll notice here that x plus 6 is the low. The derivative of the top, we slide that 7 down in front. You'll notice that we do not touch the inside here, which is 5x minus 4. We subtract 1 from the exponent that used to be there. Used to be a 7 there, now there's a 6. And then finally we multiply by the derivative of the inside. The derivative of 5x minus 4 is just 5. So this first term here is low d high. And then from that, we subtract high, which in this case is 5x minus 4 to the 7th power. The derivative of the bottom, which is x plus 6, is just 1. So that 1 there is d low. Finally, we divide that entire quantity by low squared. Now what we're going to do next is attempt to simplify this guy a little bit. So what we're going to do next is factor out a quantity 5x minus 4 quantity to the 6th power. And what that leaves in the bracketed term is 35, which is the 7 times the 5, times the quantity x plus 6. And then we have one more copy of that 5x minus 4 left over in that second term. So we get minus quantity 5x minus 4. And when we simplify what's in that bracketed term, what we end up with is quantity 5x minus 4 to the 6th power times quantity 30x plus 214, all divided by x plus 6 quantity squared. This is about as simple as it gets, and that's our final answer. Ooh, squares off a little bit there, apologies. So what we're going to do next is the final part of this last example, which is to differentiate the square root of x times ln of the square root of x. So go ahead and pause the video at this point, give this one a shot, come back after you've given it an attempt, and we'll go through it together. So you'll notice here that the first thing that I want to do is rewrite this function. Whenever we're working with square roots, it's better to write things in terms of fractional exponents because then we can apply a power rule. It's the easiest way to do this. So you'll notice here that I'm careful to distinguish my original function from its derivative. All I've done is rewritten the original function here. I've not done any calculus yet. So you'll notice that the very last operation that would take place here is the multiplication between the x to the 1/2 power and ln of x to the 1/2 power. As a result, the product rule is the first rule that we have to apply here when we do our differentiation. So once we do that, we get the derivative of the first quantity. So in other words, the derivative of x to the 1/2, which is 1/2 x to the minus 1/2 power, times the second quantity all by itself. And then we add to that x to the 1/2 power, that's the first quantity itself, the first factor itself, multiplied by the derivative of ln of x to the 1/2. So we get ln of x to the 1/2, the derivative of that guy is 1 over x to the 1/2, and you'll notice that we do not touch the inside function here, just like usual. And then at the very end, we multiply by the derivative of the inside, which is 1/2 x to the minus 1/2. You'll notice that in this second term, the x to the 1/2s cancel, and what we end up with after we change the fractional exponents back to radical notation is 1 over 2 root x times ln of root x plus 1 over 2 root x. Now that's about as nice as it's going to get, and because we started with radical notation, we're going to end with radical notation, so that's our final answer. Alright, so that just about takes care of it for the chain rule, which is good because it's starting to get dark outside. So make sure you find the PDF attached in eCampus and you drill some derivatives over the next few days. It's definitely going to take some practice to get used to it. Bring any questions that you have to the next class and we'll cover them. Good luck. Have a good spring break.